Now what I'm going to do is I'm going to illustrate this with a few examples. So this is an example of a piston mirror with 4 flexure springs. So you can see this thing has a big plate here, and we're going to assume this plate is solid. It doesn't bend, so all the bending is in these red suspension arms, and there's 4 of them. And we're going to treat each flexure spring as basically being a fixed and guided beam. Okay, so here is the force P that's applied to the end of it. And once again, this is using, I'm going to change this notation. So I'm going to say U of x is the displacement function for this flexure spring, right? So it has length L here. It's shown as big L. I'm going to write it as little script L. Okay, so this is little script L. This is the length of those flexures. And they have some width to them, W, and some thickness, T, right? So this T is the usual film thickness, and this little W is the width of the beam. And so what are we going to use for our deflection shape of this beam? I'm going to use as my function here, I'm going to use the static deflection function for a fixed guided beam with a point load. Okay, so deflection So P is the point load, right? So it's shown here. P is this. This is the point load applied to a beam. So I'll write that as U of x here is equal to 1 over 12 EI times 3L x squared minus 2x cubed times P. Okay, so the deformation to deflection depends on the amplitude of the load. And you see, again, it looks like, if you remember when we did the calculation for cantilever beam bending, we get an x squared and an x cubed term in here. So it's a polynomial in x, where x is the coordinate along the length of the beam. And the displacement at the end of the beam, which is what the mirror does, right? So the mirror displacement so basically x is equal to, I'm calling it script L here. So we get U at L is going to be equal to L cubed over 12 EI times P. So all I did was I plugged in x equals L into this formula up here. And I'm going to call this thing, I'm going to call this U naught, okay? So that's the displacement at the mirror, okay? Mirror displacement. Okay, is U naught. And so with that parameterization, I'm going to write U of x is equal to U naught over L cubed times 3L x squared, whoops, minus 2x to the third. Okay. So why did I go through that stuff here? Well, the idea is I tried to figure out some displacement function that describes the displacement of this flexure. So I looked up the deflection for a fixed guided beam, and this is the equation that I got. But now I don't want to solve for something with the displacement with a point load. So I'm going to figure out what the displacement is at the end of this mirror, and it turns out that ends up, I can use that mirror displacement as a parameter, and I end up with this as my, this is basically my trial function that I'm going to use. So I just wanted to get rid of P as a variable. And now it turns out it does not matter what U naught is, because you remember when we did when I showed the calculation, the very original derivation here, right, we end up with the amplitude of the motion appears in, it's equal in both the kinetic energy term and the elastic strain energy term. So it doesn't actually matter what U naught is, because U naught will drop out. It will appear in both the numerator and the denominator of my calculation. And so it will it will go away. Okay, so let's now go through the calculation. Well, first what I want to do is I want to find, so we're going to find the elastic energy, and we're going to find the kinetic energy. And I'm going to start with the kinetic energy. So the kinetic energy is going to be equal to the sum of the kinetic energy in the springs plus the kinetic energy from the plate or the point mass. Okay, and that one's easy to calculate. So let's start with that. So I'm going to write WK for a plate. So that's just 1/2 omega squared U naught squared times the mass of the plate. Okay? So remember, the idea here is that this is the velocity amplitude. When we do these calculations, the velocity is the frequency times the displacement, and so the velocity amplitude squared. Okay, so this is 1/2 mv squared. And the mass of the plate here, if we look at the plate here, it's got length big L, I guess is how it's written here. It's got length big L. And it's got thickness T to it. And so what I'm doing is I've got, actually, it turns out that if we think about energy here, I have the total kinetic energy is basically 4 parts, right? So I got 4 springs, and I have 4 quadrants to the mirror. And it turns out that the strain energy for each spring, it turns out I've got 4 springs, so I could divide those into, I have the strain energy for each spring individually. And so rather than calculate everything 4 times, what I'm going to do is I'm really going to analyze based on a quadrant of the device, okay? And it turns out that when I take the ratio of the kinetic energy and the elastic energy, I'm taking the ratio of just 1/4 of the whole thing. So I don't need to calculate over the whole body. So I'm just going to do all my calculations based on 1/4 of the body. And so the mass of the plate here is equal to L over 2 squared times T times rho. And so we get that WK for the plate Okay, so the WK for the plate is equal to 1/8 omega squared U naught squared times rho T L squared. Okay, so that's the kinetic energy for the plate. And now the kinetic energy for one spring. Remember, we're going to find this by integrating. So I wrote this formula on a previous slide, 1/2 omega squared times the integral from 0 to L of rho times the area, which is W times T, times U squared of X dx. Right? So this is the mass part, and then this is the displacement function squared. And so when I integrate, if I go back to, this is the function that I have to square and integrate. I'm not going to do that here in the lecture, but I'm going to give you the solution. So when I do that integral, I get this is equal to 13 omega squared over 70 rho W T L to the 7th actually, sorry, 13 omega squared over 70 rho W T L U naught squared. Okay, so that's the kinetic energy from the spring. Okay, and so the total is the sum of these two guys. won't quite fit on this slide. So WK is equal to rho T times 1/8 big L squared, that's the length of the plate, plus 13 over 70 WL times omega squared U naught squared. Okay? Now the elastic strain energy, because we only calculated the kinetic energy for 1/4 of the plate and for one spring, and so we only have to calculate the elastic energy for one spring. And so that's equal to the bending strain energy, 1/2 EI times the integral from 0 to L of d squared U dx squared quantity squared dx. So this is bending strain energy so that's from lecture 11. Okay, so we know that the bending strain energy is the square of the curvature integrated over the length of the beam multiplied by 1/2 EI. And so when we do that calculation, what we end up with is that WE is equal to 6 U naught squared times EI over L cubed. Okay, so this is the elastic strain energy in one of the springs. Okay. And so what we're going to do is we're going to equate WE and WK and solve for omega. Right, so omega is here. So I'll do that on the next slide. Oopsie, haha. I'll do that by making this a little bit bigger. And so I get WK is up here. I got rho T 1/8 L squared plus 13 over 70 W. This is W. L, oops, little L. U naught squared. Omega is equal to 6 EI over L cubed U naught squared. Okay, remember I said that the displacement amplitude didn't matter. So it looks like you see that it ends up being squared in both the elastic strain energy and it's squared in the kinetic energy term. So it cancels out. And this is exactly the same way that it did when we talked about the point mass. Okay, so when we choose these trial functions, it doesn't matter that we know what the amplitude is. Okay, so the amplitude will end up canceling out. Okay, and so now what we end up with is that omega, this is a slightly complicated formula here, omega is equal to 6 EI over L cubed divided by rho T times 1/8 L squared plus 13 over 70 W times script L here, and the whole thing square rooted. Okay, so this is our expression for the natural frequency. Okay, and if you look at this, right, remember when we said that the formula is going to include the mass, the point mass, that's what this first part here is from the mass of the plate, and then this second term here is for the spring mass, right, so that would be rho times thickness times the length of the little spring times the width of the little spring, but it's multiplied by 13/70ths, right? So whatever 13/70ths is, you could calculate that. I guess that's something like 15% of the spring or 20% of the spring mass is counted. And so if we look at the comparing a point mass model with the distributed mass model, so depending on the length of the suspension, Here it's showing that as the suspension length gets